Hello, I'm Dr. Dupre, and in this section we're going to discuss linearization and differentials. The term linearization is actually a very general term in mathematics, and it's very useful in situations where we have complex relationships and we try to reduce them in certain circumstances to simple linear relationships. In particular, in calculus, linearization of a function refers to the idea of basically taking a function, looking at its graph, and replacing that graph near a specific point on the graph by the actual tangent line. Okay, let's look at some definitions. Definitions: linearization, standard linear approximation. If f is differentiable at x equal a, then the approximating function capital L of x, which is given equal to f of a plus f prime at a times the quantity x minus a, is the linearization of f at a. The approximation f of x being approximately equal to L of x of f by capital L is the standard linear approximation of f at a. The point x equal a is the center of the approximation. Now let's look at this a second. Notice a here is to denote a fixed specific point, whereas x is a variable. In other words, we're saying f is differentiable at x equal a, but x is the variable, a is the specific value of x. And now what we're looking at here in this approximating function, capital L of x, notice f of a is a definite number. It's the value of the function at a. And f prime of a is the value of the derivative of the function at that specific x equals a. That derivative is being multiplied by the quantity x minus a. And so what we have here, in effect, if I view this as y equals an expression in x, notice number plus number times x minus a. It's in effect the point slope form of the equation of a line which passes through a comma f of a. In other words, this is the function which is giving the tangent line to the graph of f exactly at the point a comma f of a. So it's that tangent line as a function of x, which is called the linearization of f at a. Well, you know, when you draw the picture of the graph of a function and look at the tangent line, for x near that point of tangency, the tangent line and the graph of the function are going to be close. And so consequently, in calculations, if it's convenient, we can often replace the tangent line function as a function for the function itself. For instance, to make a little picture here of what's going on, in general, you might have some function whose graph is a curve, and here at a specific point on that curve would be the point a comma f of a. And so then we would have the tangent line to the graph at that point. So here we have the curve y equal f of x. Here's the tangent line, and notice if I call that line capital L, it's tangent to the graph of f at the point a comma f of a. What's its slope? Well, remember, the slope is exactly what the derivative is useful for. The slope of the tangent line is the value of the derivative at that point. So here x is equal to a. We compute f prime at a. That gives us the slope of the tangent line, and so therefore, as the equation of a line viewed as a function of x in point slope form, it's simply f of a plus the slope, which is f prime at a, times x minus a. Now notice these are definite numbers. The a here is a definite number, so f prime of a is a definite number, f of a is a definite number. And so, for instance, if I were working with a linearization of something like, for instance, just as an example, f of x equals square root x, f prime of x is then 1 over 2 square root of x. So if I wanted the linearization of this at a point A where I could easily calculate square roots. For instance, if I took x equal to 9, square root 9 is 3. I could get then f prime at 3 is 1 over 2 square root 9. Notice at any value of x, if I take a to be a value where I can compute square roots, then both these numbers are easy to compute, and so I can easily get a linearization of the square root function. Now, of course, the square root function, its graph is this parabola on its side like that, and you can notice the tangent line to the square root is going to be very close to the curve. Notice how well they approximate each other, and so consequently, if I wanted to compute, for instance, the square root of 9.1, I could easily take the linearization of the square root function at x equal 9, and I would get a very accurate approximation of the square root of 9.1. And that's the general idea in using linearization. Now let's look at an example where we calculate a linearization. Here I have the function f of x equals x plus 1 over x, and I want to calculate the linearization at the point a equals 1. So what we do is begin by differentiating the function. So f prime of x is equal to 1 plus, what's the derivative of 1 over x? Well, you can remember that's negative 1 over x squared, or you could rewrite that as x to the negative 1 and apply the power rule. In any case, we have the function and its derivative as functions of x, and we have to calculate them both at a equals 1. So to begin then, f of 1 is 1 plus 1 over 1, that's 1 plus 1, or 2. And how about f prime at 1? Well, here we have 1 plus negative 1 over 1 squared, that's 1 minus 1, which is 0. So in this case, we have a very simple linearization. Remember, the linearization in this case is going to be f of 1 plus f prime at 1 times the quantity x minus 1. So f of 1 is 2, but f prime of 1 is 0. So this 0 wipes the x out of the equation entirely, and our linearization is just L of x equals 2. In other words, our linearization is the constant function because the tangent line at the point 1 comma f of 1, which is 1 comma 2, has slope 0. Now let's look at a problem where we use linearization to make an approximation. Here I have the function f of x equal cube root of x, and what I want to do is use linearization to approximate the value of this function at the point x naught equal 8.5. Now this does not mean that I want to linearize at x naught equal 8.5. I want to choose the center of approximation to be a point as close to 8.5 as is convenient, but one for which it's very easy to compute the values of the function. After all, if computing the cube root of 8.5 is a problem, then certainly we need to find a point nearby the 8.5 where it's easy to compute cube roots. Well, can you think of one that's easy? Certainly the cube root of 8 is easy to compute because the cube root of 8 is 2. So what we can do is set A equal to 8. So not 2. The cube root of A is then equal to 2. Okay, so now what we need to do is compute the derivative. F prime of x is, well, this is x to the 1/3 power, so we can rewrite that as x to the 1/3 power. The derivative of x to the 1/3 by the power rule is 1/3 x to the negative 2/3. And so now we're going to rewrite that in ordinary radical notation. The negative brings this down into the denominator, so we have 3x to the 2/3, which means cube root of x quantity squared. And so you see the problem of computing the derivative turns out to be the same as the problem of computing the original function, namely to compute cube roots, but we've chosen our center of approximation to be a point where we can easily compute the cube root. So f prime at a is here, f prime at 8, which is 1 over 3 times the cube root of 8 quantity squared, which is 1 over, now cube root of 8 is 2, squared is 4, times 3 is 12. So f prime at a is a 12th, and that means our linearization is L of x equals the value of the function at a, which is 2, plus f prime at a 12th, times x minus a. Remember, a is 8, and so there's our linearization. So what would we get for our approximation of 8.5? L of 8.5 is simply, well, if I replace x by 8.5, I have 8.5 minus 8, well, that's a half, times a 12th is a 24th, plus 2 is 2, and a 24th. So there's our approximation of the cube root of 8.5. Now let's look at the linearization of a power function. Show that the linearization of f of x equal 1 plus x to the power k at x equals 0 is L of x equals 1 plus kx. Well, first let's notice that f at x equals 0 is simply 1 plus 0 to the power k, which is 1 to the k, which is 1. So that's pretty simple. And now let's differentiate the function. So we have f prime at x is, using the power rule, 1 plus x to the power k minus 1, and the chain rule tells us multiply by the derivative of what's inside. Well, the derivative of 1 plus x is simply 1. So what is f prime at 0? Well, if I replace the x by 0, this factor just becomes 1 to the k minus 1, which is also 1. So I have k times 1, which is simply k. And so that tells me the linearization, L of x, is equal to, remember, f of 0 plus f prime at 0 times x minus 0. We'll put in what these numbers are. F of 0 is 1, plus f prime at 0 is k. X minus 0 is just x. So there we have it. L of x is 1 plus kx for the linearization of the kth power function centered at x equals 0. In effect, what we've done by using 1 plus x here and doing this at x equals 0 is to take the center of the power function x to the k at x equal 1. So that would be the same thing as I said, okay, linearize f of x equal x to the k at the point x equal 1. Notice what this is saying here. Suppose I wanted to raise 1.1 to the third power and take the linear approximation. I used equal AP for approximately equal. Well, this is telling me it's just 1. What have I added on here? A tenth. So take that tenth and multiply by 3, so that would be approximately 1.3. Linear approximation for the power function is very simple. Right at x equal 1, you can easily calculate high powers that way. Another useful concept that's related to linearization is the concept of the differential. Let's see how that's defined. Let y equal f of x be a differentiable function. The differential dx is an independent variable. The differential dy is dy equal f prime of x dx. I want you to keep in mind here that the dx, even though it has 2 letters, it's really one thing. So in other words, the dx itself is a 2-letter symbol for one thing, and it's an independent variable. Likewise, the dy is a two-letter symbol for one single thing. It, in this situation, is in effect a dependent variable, and it's dependent on dx as well as x. If I hold the x fixed, notice that the dy just depends on dx in this very simple way. It's f prime of x multiplied by dx. But on the other hand, if I allow the x to vary as well, then the dy has a very complicated dependence on both x and this new variable dx. So we have, in effect, two independent variables occurring in this one expression. Now, another thing to notice here is that in this equation, if I divide both sides by dx, I get the equation dy over dx equals f prime of x, and you can recognize dy over dx is the Leibniz notation for the derivative. So another way to think of the differential as arising is by taking this equation, which equates the prime notation of the derivative to the Leibniz notation. Think of the Leibniz notation as truly being a fraction, and then multiply out both sides by dx. And so if I would allow, okay, there's another variable here, dx, which it makes sense to cancel, then the dx's here cancel, and so results in this equation, dy equals f prime of x dx. Now for practice, let's calculate a differential. Here I have the function y equal x cubed minus 3 times the square root of x. So remember, for the differential, we have dy equals f prime of x times dx. So in effect, all I do is just differentiate the function in the ordinary way, but instead of writing f prime of x equals the derivative, I'm going to write dy equals, start differentiating. So derivative of x cubed is 3x squared minus 3 times the derivative of square root x, which is 1 over 2 root x. And then at the end, I multiply the whole thing by dx, and that's all there is to it. Now, one thing to keep in mind here with this differential is if I were to actually take a specific value for x, because notice the differential here is a variable which depends on both the x and this new variable dx. If I were to take a specific value for x, like suppose I took x equals 4, where I can easily compute the square root of x. So if I set x equal to 4, this gives me dy equals 3 times 4, or 12, minus square root 4 is 2, times 2 is 4, so we have minus 3/4 times dx. And so we actually now get a very simple equation. Dy is 12 minus 3/4 times dx. Well, we can simplify that. That's 11 1/4. Dy equals 11 1/4 times dx. So what that in effect is telling me is that with this independent variable dx, I can think of that as being an increase in x from this initial value x equal 4. If I increase the x by some little amount dx, then this corresponding change in y we would think of as dy that depends on the change in x dx is 11 1/4 times dx, which of course is simply the result that the slope of the tangent line there is 11 1/4. Well, let's compute a differential where we have a function involving trig functions. Here we have y equals the sine of the quantity 5 times square root of x. So dy is equal to, we just differentiate. Now we'll have to apply the chain rule. Start with the outer function. Derivative of sine is cosine. Leave what's inside alone. And now multiply by the derivative of what's inside. So that's 5 times the derivative of square root x, which is 1 over 2 square root x. And the last step, remember, multiply by dx. So remember, the dx is a new independent variable, so our differential dy depends, notice it's always linear in the variable dx. It always appears simply as a factor out to the right. It's the x that appears in a complicated way. Now let's compute a differential of a function and compare it to a linearization. Here I have the function y equals tangent of x cubed over 3, and I want to find the differential of this. And so remember, all we do is differentiate and then multiply out the dx. So if I differentiate using the Leibniz notation, I have dy dx equals, and we use the chain rule, derivative of tangent is secant squared of the quantity x cubed over 3, and then we multiply everything here by the derivative of what's inside the parenthesis. Well, that's 3x squared over 3, and notice the 3's cancel, and so to get our differential dy, in effect, we just multiply both sides of this equation by dx. So finally, dy is the secant squared of the quantity x cubed over 3 multiplied by x squared dx. Well, let's look at the linearization of this at x equal a. The linearization of our original function, how would we do that? Well, we would compute the derivative at x equal a and the value of the function at x equal a. So we have f of a to compute and f prime of a, which is, of course, secant squared of a cubed over 3, all multiplied by a squared. And so to write down the linearization, we would have L of x equals f of a plus the quantity secant squared of a cubed over 3, all multiplied by a squared, and then times the quantity x minus a. Now notice what's happening here. Suppose I say, well, let's move this f of a to the left side. Then it becomes, the left side becomes L of x minus f of a equals what's on the right side. Well, notice all of this right here is the derivative. It's what I would have right here if I replace the x everywhere by an a. What have I got right here? X minus a. This is replacing the dx. And what have I got over here? L of x minus f of a. That's playing the role of the dy. So in effect, the way to compare the linearization of a function at a specific point with the equation for the differential is you can think of the differential here as representing the difference between the linear approximation of the function at the variable value x and the value of the function at the specific center of approximation. So the dy is sort of the variation in y along the linear approximation, and here you have the coefficient of the little change in x, which in this case is x minus a, corresponding to the dx. Before we finish up here, I want to point out a simple mistake that students often make when dealing with equations of tangent lines and linearization. So let's look at a simple problem. For instance, suppose the problem is to find the tangent line to the graph of f of x equals square root x, where x equals the value a, which is given to us as 4, or you want to linearize at a equals 4. And so we know we have to compute the derivative, and so we compute the derivative as f prime of x equals 1 over 2 times the square root of x. And so we all remember that the significance of the derivative is it's the slope of the tangent line. So it's the slope at the point x comma f of x. But notice x here is a variable, and so this slope here is varying with x, of course, and you see the curve here, for instance, in this case, square root of x is parabolic. The slope of the tangent line is varying from point to point. we're told to find this linearization at the specific value x equals 4. And so sometimes students will forget that you have to substitute x equal 4 in this expression for the derivative and instead write something like this. L of x equals square root of x plus 1 over 2 square root of x times x minus 4. Now, this is not the linearization of this function at x equal 4, a equal 4, and this kind of thing is certain to cause your teacher to mark your paper wrong. So be aware. This is, or I should say, nonsense, and the proper thing to do is to evaluate the function at a equal 4. In this case, we get 2 plus putting in x equal 4 here, we get square root 4 is 2 times 2 is 4, so we get a 4 down in the denominator there, a fourth for the slope of our tangent line times the quantity x minus 4, and that's the proper linearization. Notice the only place the x appears is right here as the term in the x minus 4, and that's as a simple factor. We have a degree 1 expression in x. So if you get something like this, you're forgetting something. Okay, well, now that you've seen these problems on linearization and differentials worked, you might want to try some on your own.